Hello, so today we're going to be talking about centrifugal pumps. More broadly speaking, centrifugal pumps can be described as turbo machines, which consist of blades attached to a rotor with an inlet and outlet shaft that guide the fluid flow. Then there's three different types of turbo machines. There's radial, axial, and mixed flow. In radial flow, the fluid leaves the turbo machine with a radial component to the axis, as you can see in the image on the top. Then in the bottom, in the axial flow turbo machine, the fluid leaves parallel to its axis. And then in the mixed flow turbo machine, it has a mix of both radial and axial components to the turbo machine. The reason why these are used so much is because they have a wide range of applications, from simple fans to aircraft engines, and they also have a very high power density and they're very efficient. Turbo machines can also be divided into two parts, either pumps or turbines. And as you can see in the image at the bottom, in pumps, the fluid enters the pump and the shaft is already rotating, which adds energy to the fluid and increases its kinetic energy and pressure. While on the other hand, in a turbine, it works the opposite way. And as the fluid enters it, it causes the turbine rotor to rotate and it extracts the energy from the fluid, and it decreases the fluid's kinetic energy and pressure.
So centrifugal pumps are a type of radial flow turbo machines, and it consists of two main components, the impeller and a stationary casing. The impeller consists of blades, and so the stationary casing holds the impeller. Now, how it works is that fluid comes into the eye and blades rotate, and this causes work to be done on the fluid. And this results in a large increase in kinetic energy and an increase in pressure. Now, the limitations of centrifugal pumps include that to make it very efficient, you need to make sure that the blades are at a high constant speed. And also that they can't have high viscous fluids because it reduces the efficiency. And this is because when there's a larger resistance, higher pressure is needed to continue to maintain the flow rate. Now, a problem with the pumps is cavitation. So when fluid is pumped to the eye, the pressure gets reduced, and sometimes the pressure can be too large that it causes liquid to flash to steam. And this causes bubbles that happen in the eye. And as they go towards the outside, these bubbles collapse, and this collapsing causes significant damage to the pump.
So in real life, flow through a pump is going to be unsteady in 3D, but if we consider the average one-dimensional flow through a pump, we can write that V1, the absolute velocity of the pump, is equal to U1, which is the velocity of the blade, plus W1, which is the relative velocity, or we can rewrite it as U1 is equal to R1 times omega, which is the angular velocity, so V1 equals R1 omega plus W1. If we use the moment of momentum equation to find the torque needed to rotate the impeller, we have that T shaft equals negative M1 R1 V theta 1 plus M2 R2 V theta 2, where V theta 1, V theta 2 are the tangential components of V1 and V2 respectively. And so we can rewrite it as T shaft equals M R2 V theta 2 minus R1 V theta 1 if we take the mass flow rate, or we can rewrite it as T shaft equals density times volumetric flow rate times R2 V theta 2 minus R1 V theta 1. And then to find the power transfer W, we know that W shaft equals T shaft times omega. And since we know that U1 equals R1 omega, we can rewrite it as W shaft equals rho Q U2 V theta 2 minus U1 V theta 1. And if we divide out by mass, we get that the work per unit mass equals U2 V theta 2 minus U1 V theta 1. Using Bernoulli's equation, we can rewrite this as U2 V theta 2 minus U1 V theta 1 over G equals H out minus Hn plus HL, where the H out and Hn are equal to pressure over rho G plus V squared over 2G plus Z, and HL is the loss over gravity. Now, in the ideal situation, obviously we won't have loss, so the maximum head rise can be written as U2 V theta 2 minus U1 V theta 1 over gravity, Or when V theta 1 is equal to 0, which is often the case, we just have that the maximum head rise is HI equals U2 V theta 2 over G.
So pump performance characteristics are classified by a few different parameters. The actual head rise and the flow rate are determined experimentally, and the equation and the setup to calculate head rise is shown. But perhaps the most important pump parameter is pump efficiency, denoted by Greek letter lowercase eta. This is calculated as the ratio between power gained by the fluid and shaft power driving the pump. The overall efficiency of a pump stems from three different sources: hydraulic efficiency, mechanical efficiency, and volumetric efficiency. And since it's a bit difficult to analyze the performance of a given pump just by looking at equations and numbers, typically the performance characteristics are represented by curves, typically relating efficiency, head, flow rate, and brake horsepower, also known as BHP. This is shown in the plot on the lower right, and a few things can be determined from this plot. For example, the maximum efficiency occurs at a certain flow rate, denoted as the normal or the design flow rate. And these curves help engineers in their selection of pumps for a given process because they want the pump to operate at the design flow rate. This slide includes actual examples of pumps in industry. These photos were taken by me when I was on a co-op at a linerboard paper mill last semester. Typically, centrifugal pumps are used to pump fluids such as water and other low viscosity fluids such as acids and bases, for example. The size and the power of the pump, as well as the motor, determine how much fluid can be transported per unit time. Both of the pumps in the photos are in fact centrifugal pumps. The pump on the top pumps a dilution liquid that's similar in viscosity to water. The blue part is the actual pump, and behind it is the motor. The discharge flow rate for this pump is around 2,000 gallons per minute, so it's a small to medium-sized pump. The pump on the bottom is a smaller pump used for high concentration sulfuric acid, and you can actually see a major leak in the photo. So acid was leaking both out of the discharge valve and also out of the casing. So this is not only an equipment failure, but also a safety concern because sulfuric acid is very dangerous to be around, especially in high concentrations. This is why it's very important for engineers to understand how pumps work with all of the different components. So that way in a situation like this, they can act immediately to prevent further exposure to a dangerous acid. In addition, proper knowledge of pumps also helps prevent issues such as cavitation from occurring.